The method for solving quadratics that we're going to learn for Algebra 2 is called completing the square. And technically, if we were to derive the quadratic formula, you would see this kind of in action in the quadratic formula. And then you would see why the quadratic formula always works. Now, turns out for a lot of kids, this turns out to be one of their favorite methods for solving a quadratic. Sometimes you don't want to use this method for every quadratic. We'll talk about when you want to use completing the square. Oftentimes I'll just say you have to solve a certain quadratic by completing the square. So it's a skill set that you have to have. We're actually going to use completing the square techniques on other types of problems as well. So it's like a three-part lesson. We're going to do 2 of them today. So first, we have to learn what it means to complete a trinomial into what we call a perfect square trinomial that we could write as a perfect square binomial. So the way the pattern works is if you have, and this is the important part, this first term has to be a 1x squared. And if I was able to create it in a way where the trinomial is x squared and then plus some number bx, and then this last number is half of b squared, we have what's called a perfect square trinomial. And this always factors into this pattern. So the goal is if you could make that happen, then the factorization becomes really easy. And then turns out what we have done now is created a problem where we can go ahead and square root both sides of the equation, which is a very easy way to solve quadratic. Let's talk a little bit about how we can complete the trinomials to make that happen. So the pattern that we're going to be using is you take your b term, whatever it is, you cut it in half, and then whatever that number is, you're going to square it. And that's how we create what we're going to call the end of the trinomial, the constant. So our b term in this problem is this coefficient -8. And by the way, I should have prefaced it with all of the a values in these quadratics are 1s. So it has to be a 1x squared, 1x squared, 1x squared for this to work. So back to the formula. You take the b term, which is -8. You're going to cut it in half. And then we're going to square that value. So -4 squared is a positive 16. And that is what we're going to use in place of the c. So if I rewrite this trinomial as x squared minus 8x plus 16, what you're going to see is that's a really easy factoring quadratic. It's x minus 4 times x minus 4. So the way we'd write that is x minus 4 quantity squared. So I've purposely designed the trinomial so that it always factors into, it's going to be x, and then you're going to take half of your b term, and then the quantity is going to be squared. It's going to be the factorization. So if you feel like factoring is a struggle for you today, it's going to be really easy because it's the same factoring pattern over and over and over again because of the way we've designed it. This one's a little exciting because the b term is not a pretty number when you cut it in half. So -3, cutting that in half, instead of writing that as a decimal, we're going to leave it as a fraction. So -3 cut in half, let's just call it -3/2. And then when I square that, it's a lot easier to do this math of fractions. So squaring -3/2 is positive 9/4. So that is the c value that we're going to use. So my new trinomial is x squared minus 3x now plus 9/4. And then using my factoring pattern, it's x. And then remember, half of the b was -3/2. So minus 3/2. Quantity squared is the factorization. So this next one, same idea. Our middle term b is 26, positive 26 this time. So 26 cut in half, which is 13. And then we squared that. I think we get 169. So that is the value for c that'll make this a perfect trinomial. So my new trinomial is x squared plus 26x plus 169. And then the quantity, when I factor that into quantity squared, it's going to be x. And then half of the b term was positive 13. Quantity squared. There you go. So that's how we can magically create a trinomial that factors nicely into that pattern. So now how can we use that skill to actually solve an equation if it's quadratic? So this is our current quadratic. It does not follow that pattern because half of 10 is 5, 5 squared is 25, not -3. So what we can do is we can manipulate the equation so that it does have that perfect square trinomial factor, and then we can square root both sides. So the first thing you have to check is that your a value is a 1, which it is. If it's not a 1, you'd have to divide everything by whatever that a value is. But for the future, if I have to do that, and it turns out to be like funky fractions everywhere, then maybe it turns out that's not the best method for solving this quadratic. Every quadratic can be solved with completing the square, but fractions make your factoring kind of messy, so just remember that. But our first step after that is now to write it in the form x squared plus bx and then adding blanks. So basically we're setting up the trinomial so that I can complete it and make it into this perfect square factor. This constant that was originally in the problem is actually going to move to the other side of the equation. So if I add it over, it's now a positive 3. If you think about equation law, if you add something to the left, you have to also add something to the right. So we're going to keep things balanced by putting a plus blank on both sides of the equal sign. So now remember, I can do whatever I want to an equation. So if I was to magically create that value for, we called that c, I would take half of 10 and then square that. So that's 5 squared, so 25. And that's what I'm going to put in place of the c value. But if I add 25 to the left side, I have to also add 25 to the right side of the equation. So you might ask yourself, like, why? Why'd you do that? Because watch what happens now. This perfect trinomial is going to factor into x plus 5 quantity squared. And then over here on the right-hand side, 3 plus 25, better known as 28. And look at that. We have an equation that we can square root both sides. So let's do that. And remember, the moment you square root in an equation, the answer on the other side of the equal sign is not just positive, it's also negative. So right now we have x plus 5, because the squared square roots cancel. And then plus or minus 28 breaks into 4 times 7. 2, and then square root of 7 does not break down. And then our last step is to subtract this 5 from both sides of the equation. So our solution set is it's not rational, so we'll just write it as negative 5 plus and minus 2 square root of 7. So you did just get two answers. You got negative 5 plus 2 square root of 7 and negative 5 minus 2 square root of 7. Both correct for this context. If it was a story problem, possible one of them isn't correct, but we'll get to that problem later. So my next question does have a 1 coefficient, so we're good to go there. But I am going to take this original constant and move it to the other side because right now, as it sits, it's not a perfect square trinomial. So when I add the 8 over, since I'm rewriting it, I'll go ahead and add those blanks. I don't know if you can hear my son in the background singing. Very loud. All right. And remember, we added the 8 over. So half of your b term, and then squared would be 3 squared, so 9. So adding 9 to both sides. I'm going to pause the video, tell them to be quiet. Alright, so now this trinomial is a perfect square trinomial. It can factor into x plus 3 quantity squared, and then 8 plus 9 is 17. This is my favorite kind of completing the square question because when I go to take the square root of 17, that cannot break down at all. So we'll say this is x plus 3 equals, don't forget your plus or minus in front of the solution, square root of 17. And then I just subtract the 3 over. So I can't combine the 3 with the square root of 17, so we write negative 3 plus and minus square root of 17. So fun fact, had you done what we're going to learn is quadratic formula, same answer. Obviously these can't be factored because, at least not easily, you won't be factoring with 3 plus and minus square root of 17. But a lot of kids end up, if given a choice, they like completing the square, so they choose it if it's not too bad of a problem, meaning no fraction. All right, so again, 1 is my first coefficient, good to go there. We are going to move this original constant over, and we're going to add a blank as we rewrite it so we can complete the square. So x squared minus 12x, and then plus something, and then remember we subtracted the 4 over, and then keep your equation balanced. So what goes in that blank is going to be, you take your b value and then cut it in half and then square it. Now I know the negative is going to cancel out when you square it, but I always write it down because it helps me on my factoring step to not forget that the factor is a negative number. So negative 6 squared is positive 36. The whole reason we did that was because now this trinomial can factor into x, and then half of b was negative 6 squared. Negative 4 plus 36 is 32. Okay, so a bit of bad news when we square root 32, that's going to need to be broken down. So 32 does have a couple of perfect squares as factors, but you want to go for the biggest one so you don't have to do too much work. 32 is 16 times 2. So this becomes 4 square roots of 2. So this is x minus 6 equals positive and negative 4 times square root of 2. And then final answers, when you add the 6 over, 6 plus and minus, oops, 4 times the square root of 2. So again, we're getting 2 solutions. All of them so far have been irrational. But in theory, they could be nice, like 2 plus and minus 7 might show up because the radical totally breaks down. And then in that case, you just have to add 2 plus 7 to minus 7. So take a look here. It's kind of nice. They went ahead and they already had the constant moved over. Calculating the c value is you take half of the b term, then we square it. So 7 squared is 49. Whoops. Switched colors on myself. All right, so 49 added to both sides of the equation. And the reason we did that is because now this trinomial can be factored into a perfect square binomial, x plus 7 quantity squared. And then negative 57 plus 49 is, oh, that's negative. This is a typo. Let's call this 57. You guys don't know about i's yet. So we're just going to go ahead and change that. The teacher, I can do that. All right, so let's see. That's 106. All right. So then when I square root both sides, let's see. 106 is not divisible by 4 because 100 is. Digits add up to 7. I don't think it's reducible at all. So we end up with x plus 7 equals plus and minus the square root of 106. Sorry about the typo. Now, had we already learned about complex numbers, imaginary numbers, probably could have finished the original problem, but alas, we'll have to wait. We're going to learn about complex numbers soon, and then we're going to redo all these methods with solutions that are called imaginary or complex solutions. It's going to be a good time. All right, moving on. Oh, bad news. All right, so the first coefficient is a 1. However, when I set this up for completing the square, and I go to find what the c value, the one that goes in the blank, we are going to have a fraction because we have 5 over 2, which I know is 2.5, but remember I said fractions are better to do all this math with. So if you square 5 over 2, you would just square the numerator and the denominator and get 25 over 4. Now I know that doesn't feel like a better answer, but it's going to be, I promise. All right, so 25 over 4 on both sides of the equation. The factorization pattern is still the same. It's still x and then plus half of b. So that was the 5 over 2, quantity squared. And then, 5th grader, adding 2 fractions together, they'd have to get common denominators. So 4 fourths plus 25 fourths is 29 fourths with common denominators. So this is why I prefer fractions for this problem, because now when I go to square root both sides, you can square root the numerator and denominator of a fraction separately. 29 doesn't break down, but square root of 4 does, and that's going to cause me to not have to worry about rationalization. And it's also, fun fact, going to give me common denominators on my next step. So x plus 5 over 2 equals plus and minus the square root of 29. And then instead of saying the square root of 4, I'm going to just call that a 2. So now when I subtract the 5 halves over, an acceptable set of answers would be negative 5 halves plus and minus square root of 29 halves. Or, since they have common denominators, you can say negative 5 plus and minus square root of 29, all of it over a common 2. And when we learn quadratic formula, this is the answer that you're going to get when you use quadratic formula, but they're the same answers. So it's fun that they're all kind of derivatives of each other. Remember the very first rule here is that you can only do this method if the first coefficient is a 1. Well, not. So we can fix this though, since it's an equation. If you go ahead and divide everybody by a 3, totally change the problem, but it's an okay thing to do in math because it was an equation. So this is a linear combination, or a combination of this original quadratic, not linear, but the solutions are going to be in the same place. The graphs would have looked a little different, but that doesn't matter for the solutions. So now when I'm completing the square, that 4 is not going to help me any, so I'm going to move the 4 over. Oh man, we're going to get another one with a complex answer. Okay, so Abruzzo is going to take the liberty of changing the original problem. Make this a minus 12, which makes this a plus 4. Gosh, I'm so glad I'm pre-recording this, and now I'm going to fix all those typos. Sorry. All right, so we're going to add a blank on both sides. I know some of you have no idea why I just got upset with myself that I had to change that, but trust me, I had to change it. So half of b, and then squared would be 1 squared, so 1. All right, here we go. So this becomes x minus 1 quantity squared equals 5. And this is super good news because when I go to square root, I'm not going to be able to reduce, which means I am nearly done. X minus 1 equals plus and minus square root of 5. And then adding that 1 over, my solutions are x plus square root of 5 and x minus square root of 5, or 1 plus square root of 5, 1 minus square root of 5, which I just write them in the shortcut 1 plus and minus square root of 5. Alrighty. So let's see if this one works out nicely. Probably not. Alright, so let's divide by 5 everywhere. X squared minus 2x. I did it again. For Pete's sake, make this a minus. I don't even know what I was thinking, man. Oh well. Alright, so that is now a minus 6 because I changed it. Okay, Scout's honor, I will totally change this document before I teach my kids, I promise. X squared minus 2x. Well, it's pretty boring because it's like the same problem again. A little different though. Alright, so putting half of negative 2 and then squaring it, we're going to get a 1 again. Ah, jeez. So there's a good chance that if you're watching this for my class and I've changed the document already, I might have even changed it to a different problem just so we had a little variety. So apologies in advance if this doesn't match your problem exactly. Go ahead and pause the video if it doesn't match yours and try to work your way to the correct answer for the version that you're looking at. The process, however, is always the same. So x minus 1 equals, good news for this problem, square root of 7 does not break down. So my solutions would be 1 plus and minus the square root of 7. I think I was probably trying to come up with a problem that came out to nice, like, rational answers. Let's see if the next one does. I don't even know if there is another one. Let's find out. Nothing works today. Okay. Yeah. Okay, I'm going to back up a second, and I'm going to pretend to make up a problem that totally what I was hoping it would be. So let's say I had x squared, let's do minus 5x plus 6. Oh, that's gross. I don't want to do that. Minus 6x plus 8. And we wanted to solve through completing the square. So again, not on your paper. Maybe it is on your paper by now. Maybe I changed it. So I subtracted the 8 over. And in the blank here would be half of this squared. So that'd be negative 3 squared. So that'd be a 9. I just want to show you what it looks like when there's no more radical. So we got x minus 3 squared equals 1. So when I go to square root both sides, 1 does break down. The square root of 1 is 1. So we write x minus 3 equals positive and negative. I'm not going to say square root of 1. I'll just say 1. So then sometimes I get kids who leave their answers like this, which, like, it's correct, but you're better than this, guys. What is 3 plus 1 is 4. And then 3 minus 1 is negative. No, it's 2. 2. So if you get to the point where your radicals reduce all the way to integers, I expect to see 2 separated answers listed out. You know, x equals this, x equals that. Because what's the whole point of doing this if you can't, like, talk to a human in human form about what the solutions are? Okay, so this is very likely the second day to our lesson. We probably just solved on the first day. So if you just missed the first day, go ahead and stop the video here. But for the second day, we're going to use kind of a modified completing the square approach to write our quadratics that are currently in standard form into vertex form. So through the magic of math, we're going to create vertex form, which remember is x minus h quantity squared plus k. So you can kind of see like there's a component that has to be completed for squaring, and then there's some weird plus k value. We're going to see where all that comes from. So, little different. We're not going to touch both sides of the equal sign today. We're going to just keep y equals over here. And it's not going to take us too long to actually get this problem finished. These are a little easier than solving because you don't have to take it all the way to the solution. It's complicated though in a sense where you have to ignore part of the problem. So right here, all I want you to do is think about the first two terms, the ax squared plus bx. That is the part that I want you to complete. So if I was going to ask you to come up with a value for c, that's what we're going to do. Now remember, there was still a plus 11 off to the side. He is not a part of that part of the problem. He's just kind of hanging off to the side. But remember, before we were adding blanks to both sides of the equation sign. Another way to keep things balanced is instead of just adding a blank on both sides, you can add a blank and also subtract a blank on the same side of the equal sign. So usually when I say that, an Algebra 2 student stands up and says, why? Why would you add and then subtract a minute later? Because I'm going to selectively group them, and you'll see how this works. So let's figure out what goes in that blank. You're supposed to take half of your b term here, so negative 8 cut in half, and then squared is 16. Negative 4 squared. So this blank is a plus 16, and then a few blanks later, you're also going to subtract the 16. So remember, this trinomial that you came up with, that you completed, is factorable into that really beautiful pattern of x minus half of b, or x plus half of b. So in this case, it's x minus 4 quantity squared. And then off to the side, after that green box, you just have 11 minus 16, which is negative 5. Ladies and gentlemen, I think we're there. Vertex form. So if I said, where's your vertex? It's at positive 4, negative 5. That's kind of brilliant, because the other way to find a vertex, remember, from our lesson on 4142, is to take negative b and divide it by 2a. And then once you figured that out, you have to go plug it back into the equation and figure out what happens when you plug that into your function. I mean, it's not the end of the world. You can still find vertex that way. But man, completing the square is kind of a neat technique, and kids seem to enjoy it. So why not have a couple of things in your math tool belt there? All right, same idea here. We're not going to touch the left side of the equal sign. We're just going to keep that as y equals for both steps. And we're going to strategically, oh, guys, I don't know if I have to do anything. What's half of this? That'd be 3. 3 squared is 9. It's already completed. So this is x plus 3 quantity squared plus nothing. So, well, that was kind of dumb. Good chance I changed that problem on the notes too. Man, I guess I didn't proofread this before I sent it out. My vertex is located at negative 3, 0. Now, if you didn't notice that was already a completed square, it wouldn't have been the end of the world. You would have like put a plus 9 and minus 9 to the other side of it, and your plus 9 and minus 9 would have canceled on the far right side of the equal sign. Weird question. Sorry about that. All right, let's try another one. This one won't be as weird. It'll be a nice normal one for us. All right, so again, we're going to selectively group, just use this part, and then kind of shuffle the plus 8 off to the side. So x squared minus 4x, I'm going to complete his square. And then the plus 8 is off to the side. But then to keep things balanced, whatever I just added in this blue blank, I have to also subtract on the same side. So half of negative 4, negative 2, and then squaring it is 4. So this blank I'm adding 4, and this blank I'm subtracting 4. And we did that because this trinomial can be written as x minus 2 quantity squared, and then 8 minus 4, better known as plus 4. So my vertex is at positive 2, positive 4. Okay, one more. All right, so y equals, and this is a good technique to practice because there's a lesson coming up on circles where you have to complete the square. In fact, not just once, but twice within every problem. So even if you're not convinced that you'll use this method if you left to your own devices, I'm I'll practice it anyways. So a half of this is 6. 6 squared is 36, and I'm kind of running out of room, so I'm going to write really tiny, minus 3, and then we're also going to minus 36 to keep it balanced. So x squared minus 12x plus 36 factors into x plus 6 squared. And then negative 3 minus 36 is a minus 39. So our vertex is located at negative 6, negative 39. I think there's a question, like, so very close to that on pretty much every summative coming up here, including the big one that you're going to take at the end of your course. So completing the square is a technique that we could use to solve quadratics. All can be solved through this technique. It's just not wise to solve every quadratic through this technique that we'll find in the future. But the technique of completing the square can help us find vertex form. It could also help us find the standard form of a circle, which is one of our upcoming lessons that you guys will, I hope, like. All right, good luck.